Hi, my name is Jennifer, and today I'm going to discuss the fourth law of Physics 1, which examines a spring's energy and position in a two-dimensional space. Firstly, we can look at the video of the system and consider which physics principles we should apply to predict the motion, as well as how to apply them. We can see that the system is made up of the spring and the mass, and the spring-mass system experiences a displacement in both the x and y positions. In order to model a prediction for this motion, we will, as usual, employ Newton's second law to iterate through the position and velocity update formulas. There are two main forces acting on the spring mass system, the gravitational force from the Earth and the spring force. The gravitational force points downward, and the spring force points toward the attachment point for all positions. Next, we are also interested in modeling the energy of the system over time. The components of the energy in this situation include kinetic energy, gravitational potential energy, and spring potential energy. The amount of energy in each form can be calculated as shown. Notably, the kinetic energy is proportional to the velocity of the system, the gravitational potential energy is proportional to the height of the system from the ground, and the spring potential energy is proportional to the stretch of the spring. The total energy of the system is the sum of all the previously discussed energies. Therefore, the change in the total energy is equal to the sum of the changes of individual energies. Due to the law of conservation of energy, the change in total energy will be zero when the system is defined as the spring mass system as well as the Earth, since energy cannot be created nor destroyed. We can import our video into Tracker to gather experimental data about the position of the mass over time. Some important choices made here include that the origin of the coordinate plane is at the spring's fixed attachment point, with the positive x direction being to the right and the positive y being up. We were given that the length of the spring at rest with the mass was 0.7 meters, which initialized the distance. X and Y position data were gathered from the fifth frame, where the mass was released, until the end of the video. Now we are ready to begin our computational model. The goal of this program is to compare the experimental spring motion with the predicted motion, as well as display the system's energies over time. The first bit of code we manipulate from the starter code is some initialization. We know the given mass of the item attached to the spring is 0.402 kilograms, and the first recorded position of the ball is given as well. The initial velocity for the x and y positions were calculated by subtracting the first position from the second, then dividing by the time between frames, which was 0.095 seconds. Next, we plug in some more initial values. The value of little g is 9.8 meters per second squared near Earth's surface. The spring constant can be calculated using information from the first frame of the video, as shown. The length of the spring at any given time is equal to the position of the mass minus the spring position. The variable s is defined as the difference between the current length of the spring and its rest length. The initial energy states are plugged in as described previously. Finally, the model loops through positions and energies for every time point with delta t as 1 over 210 seconds. The model runs for about 9.03 seconds, since that is the length of the experimental video analysis. Notably, the gravitational and spring forces are calculated for each iteration, since the spring force is variable due to the different stretches and compressions of the spring over time. Therefore, the net force changes over time. The net force is applied to the position and velocity update formulas to track the position over time. Additionally, the energies from the previous point are subtracted from each new position's energy to determine changes in energy. The result of the program shows that the expected and actual position follow each other relatively closely. However, some noticeable differences include that the experimental positions in both directions are not quite as large as the prediction. One cause of this may be a drag force from the air molecules, and it could be reduced by incorporating the drag force into the net force. Another issue is the fact that the experimental graph is not smooth due to the large time difference between frames. This could be remedied by using a different camera with a higher frame rate. The other resultant graph from the program compares all of the energies over time. Noticeably, the overall change in energy is always zero due to the law of conservation of energy. The sign of the gravitational potential energy is always opposite to the sign of the spring potential energy, since a larger spring stretch means being closer to Earth. The energy principle states that the change in energy of the surroundings plus the change in energy of the system should equal zero. The spring potential energy plus the kinetic energy can be thought of as the system's energy, since they are components of the spring mass system. Gravitational potential energy would then be the energy of the surroundings. Since the total change in energy is zero overall, we can see that this model satisfies the energy principle. Lastly, we want to compare the periods of our experimental data in both the x and y directions. Period can be defined as the amount of time it takes to make one full oscillation. We can use our graphs and tracker to see at what time the position returns to its initial location, and that is the estimate of the period. The x direction period is 1.615 seconds, and the y direction period is 1.52 seconds. The fact that the x period is slightly longer may indicate that the force in the y direction is greater, promoting greater change in velocity by more quickly applying the momentum principle. Thank you for watching. My code is linked in the description if you wish to explore further.